Okay, so um, can someone tell me? So for this first question here, find two numbers whose difference is 100 and whose product is a minimum. Can someone say two equations that satisfy these clauses? So someone give me a clause or a math equation for difference is 100 and product, and we'll think about product. Yeah, so this is for number two. Yeah, let x and y be any two numbers. So x minus y is equal to 100 is a true statement. That's what we want. We want to find two numbers whose difference is 100. Okay, and what we want is a product that is minimum. So we have a function product of xy is equal to xy. So our goal is to minimize. But we don't really like two variable functions, right? So how could you make this into a one variable function, this product function? How can you turn this into a one variable function? How can I get rid of one of the variables, x or y? Yes. So using this first statement, it must always be true because that's the condition that two numbers whose difference is 100. Then one of the numbers, x, is always 100 plus the other number. So this turns p of x y into p of x, or y. P of y equals, instead of x, we put 100 plus y times y. So p of y is equal to y squared plus 100y. So this is the product of any two numbers that differs by 100. That differ by 100. Okay, can someone tell me, in pre-calculus, how could you find the y value such that p of y is minimal? And say why does a minimum exist, etc. So which y minimizes p of y? Do you remember? First of all, can someone say why a minimum must exist without doing any derivative? So a hint is, what type of function is p of y? If you were to graph it, what would it look like? It's a parabola. Why do you know it has a minimum? You remember the inspection to see when a parabola has a minimum or has a maximum? What do you look at to determine minimum or maximum? Without derivative. It's kind of a pre-calculus method. So there's one thing here. I'll give you a hint, positive/negative. So positive tells you one thing, and negative tells you another thing. So they're both positive here. What positive number tells you this thing has a minimum? You remember from pre-calc? Does P of y curve up or curve down? If you were to graph it. Up. And why up? What tells you up? Well, if this was minus, it would still be up, and it's no longer positive. What's positive? Yeah, the leading term is positive. By the coefficient of the y squared term. It's important to remember these, quick facts because they can help you, when you actually do the calculus. Okay, so, okay, can someone tell me the pre-calculus formula for determining this minimum value? Can someone tell me what does the name of the minimum value? It has a name, the point where it's minimal. It has a specific name. Vertex, yeah. Does anyone remember what the vertex formula is? Hint, if you don't remember, you can derive it using calculus. That's the vertex form of a parabola. That's something else, which is also important. But how do you find the vertex using the standard form? So ax squared plus bx plus c. Yeah, what's the vertex there? So you're absolutely right. That is the vertex form. Yes, it's negative b over 2a. X equals negative b over 2a is the vertex. All right, can we say, how do you prove that's the vertex using calculus? What is true about the vertex of a parabola? Why is it special in terms of things we've been talking about? Yeah, it's a local minimum, right? So if we find the derivative, set it equal to 0, which let's do that. So f of x equals x squared plus bx plus c. F prime of x is equal to 2ax plus b. So set equal to 0, we have 0 is equal to 2ax plus b. And negative b over 2a is equal to x. So we know that parabolas only have minimums or maximums. So, and the only place where the derivative is 0 in a parabola, that's vertex. So that's why it's negative b over 2a. Okay, so now let's do it for this problem. So our p of y is equal to y squared plus 100y. So to minimize this, we look at the derivative. And set it equal to 0. So that's where extreme values happen. Okay, so negative 50 must be the y value. Is my answer, is that my answer? Or do I need to do something else? Just a word problem, reading comprehension? What else do I need to do? Yeah, I also need to find x. So I know that x minus y is equal to 100. So x minus negative 50. So that's x plus 50. So x equals 50. So what's the minimal product if that was a question? The minimal product is negative 50 squared. All right. So if you notice, right, we didn't really learn anything new right now. We're just finding a local min of this function. And that's it, right? It's the only local min. We could even do, so we could, if this is y plus 100, do the first derivative test to really tell us that it is actually a min. What is the derivative? Sorry, maybe I should have, not this one I care about, but this one. Okay, so to the left of 50, it's obvious that it's negative, and then it's positive, so that means it's a minimum. Okay, yeah, so we didn't really do anything new. This is first derivative test, finding a minimum, but now it's just of a word problem. Okay, so let's do the second one. Find two positive numbers whose product is 100 and whose sum is a minimum. So someone type out this statement, and then we want to minimize the sum. So we want two positive numbers whose product is 100 and whose sum is minimum. So we have two things. We have x, or three things. xy, x and y are greater than 0. We have that their product is 100. And what we want to do is look at, what is it, sum? Then maybe say s of xy is equal to x plus y. And we want to minimize this. Okay. Any questions on this setup? So we have all the info we need. So I want to minimize the s function, but I have two variables. So what do I do? Yeah, so in this second piece of information, we have y is equal to 100 divided by x. So that makes s of xy. We can turn that into s of x is equal to x plus 100 over x. So now we minimize this. Okay, how do you minimize it? Yeah, so we really want to find local mins. Okay, so s prime is equal to 1 plus, and then how do you do the derivative of 1 over x? Good, yeah, so it's 100x, I think you meant -1. And then just by the power rule, it's -x to the -2. So 101 minus 100 over x squared. Okay. So what it might be nice to do is combine the fraction. I always recommend combining the fraction. Okay, so what's next? So we want to minimize. So what is the derivative? We want to find local mins. So what do you do? What do you do with the derivative? Yeah, so we want to find these critical numbers. So which, by the way, you can factor this. So which critical number is good? There's a couple of critical numbers here, right? Which one do you care about? I claim there's only one you really care about. 10, yeah. Why not -10 and why not 0? Yes, our domain that we care about is positive numbers, specifically not 0 and specifically not negative. Good. All right, so x equals 10 is the minimizing x value. Okay, so then we find, so that means y equals 10 is the, right, 10y is equal to 100. So y is equal to 10. So the minimum value, minimum sum is 20. Okay. So any questions about that? So this one you could not do in pre-calc, right? Because it's not a parabola. Really, that's the only thing you know how to minimize in pre-calc is a parabola. But now we can do a lot more. Okay, so any questions on these first two? All right. Next one. All right, this one should look familiar if you've taken pre-calculus here. A farmer wants to fence an area of 1.5 million square feet in a rectangular field and then divide it in half with the fence parallel to one of the sides of the rectangle. How can you do this so as to minimize the cost of the fence? Okay, so let's think about some key pieces of information. So what's fixed is that the area needs to be 1.5. I'm going to forget about million. The units are in million. Another thing we also need is the field, or whatever it is, needs to be in a rectangle. And we also have this secondary condition, is that it needs to be divided in half with the fence parallel to the one on the sides. So we draw this. So we have a rectangle. And so if we have to divide it in half with the fence parallel to one of the sides, there's two ways you can do it, and they're both equal. To divide it this way, or to divide it this way. But let's just choose one. let's divide it this way. And in particular, it's half. So that is something we should keep in mind. So what we want to do is minimize the cost of the fence. Okay, so what can we do? Let's give letters to some things. Let's have this be the width of the rectangle. And this be the length of the rectangle. So what do you know about, so what do you know? What do you want to find out? What do you know? What must be true? What are you trying to minimize? Someone give me a piece of information. Maybe call it W and L. Good, yeah, so W times L must always be 1.5, always. So we can adjust the lengths and widths as long as the area is fixed to be 1.5. Okay, so what are we trying to do? We're trying to minimize the cost of the fence. So we can just speak like normal. What would it take to minimize the cost of the fence? Like, in other words, you're saying you want to buy the least amount of fencing, right? So if you want to buy the least amount of fencing, someone give me an equation to minimize. Or at least someone give me an equation for the total fencing. Yeah, 3W plus 2L. So by the way, we've already established the constraints. This half thing was actually kind of a red herring, right? It doesn't matter really where you place this parallel, right? It's always going to be 3W plus 2L, and the area is still going to be the same. So the half didn't really matter for this. Okay, so how do you minimize this? So really, the hardest part of this is just to set it up, right? Now that we have the setup, what do you do? So if you want, we can say, let's do P for perimeter. We have P of WL is equal to 3W plus 2L. This is two variables, so how do you make it to one variable? And which variables may be easier to solve for? I think L is easier, right? Because 1.5 times 2 is 3. 1.5 times 3, that's still a decimal, right? I don't know. It doesn't matter either way, but I'm going to solve for L just because I don't like decimals. Do you see why? because when you substitute in for L, you get 3. So it's 3W plus 3 divided by W. So any questions on this step? All right. All right, so what do? Might be good to combine fractions first. So we have 3W squared plus 3 divided by W. Okay, let's find the derivative, right? That's what we're here for. We're trying to minimize this. So P prime is, the derivative of the numerator is 6W, then times the denominator W, minus derivative of the denominator is 1, and then 3W plus squared plus 2, 3, divided by W squared. All right, so this is 6W squared minus 3W squared minus 3, which gives you 3W squared minus 3 divided by W squared, or 3W squared minus 1 over W squared. Okay, what do you do with this derivative? I'll say it for you. Set it equal to 0. But someone else tell me what W I like. Which W is the one I care about? Yeah. This is the only one I care about, right? If I have a 0W, then my area is 0. That doesn't make sense. Negative width also does not make sense. Okay, so W is equal to 1. Remember, this is in millions. Or, what was it in million square feet? So this is million feet. Okay, so what do we want to do? We want to find... Okay, so the other thing we need to find is length, right? So W times length is always 1.5. So L is equal to 1.5. Okay. So these are the dimensions, 1 and 1.5. Okay, any questions about that? Okay. So let's go on to the next one. All right, this one's a bit different. Okay, we have a box with a square base and an open top, and it must have a volume of 32,000 centimeters cubed. The question is to find the dimensions of the box that minimize the amount of material used. Okay, so someone give me some info. First of all, what? So it's volume of 32,000. What's the volume of what? Of a box, right? What's a formula for the volume of this box? Doesn't need to be S cubed. That's a cube. I agree that something must be the same. It's close. Right. All the only constraint is that the box is a square base. So if you have a square base, right, the height could be anything. It's still a box. Right, so this is the square base. You can have S, and then the height of the box. Okay, so the area, or not area, what we're talking about, volume, is 32,000 is S squared times H. Okay, so we want to find the dimensions of the box, so we want to find S and H that minimize the amount of material used. Okay, so how do you know how much material is used? So if you don't know the formula, at least say maybe what you would want, and we can figure out the formula. So like what constitutes material? Good, yeah. And I like that you specifically did not say the top also, right? Because the top is open. Okay, so the amount of material is just if it's like cardboard or something. So that's exactly surface area. And also the base. Yeah, so then the surface area is area of base, which is just S squared. And then the sides of the box, what is the area of the sides of the box? Right, they're each SH, and there's 4 of them. Okay, so this is the one that we would need to minimize. Okay, so what do? What's the easier variable to solve for? Etc. Right, you have a 2-variable equation, SA, in terms of S and H. So how do you get rid of one of the variables, and which variable should you get rid of, and which variable shouldn't you get rid of? Yeah, H is probably the easier one. I mean, you could do S as well. But yeah, there's a problem with S because you'd have the square root, right? So don't solve. Yeah, so solve for H. So 32,000 divided by S squared is equal to H. So SA of S is equal to S squared plus 4S 32,000 over S squared. Um, 4 times 32, something, 128. Okay, so this is, that's an S, by the way. S cubed plus 128,000 over S is equal to SA of S. All right. Is 128 a perfect cube? Anybody know? Can you cube root 128? No. Oh, s cubed. I was combining the fractions. This s squared was here from the beginning, and then do you see that I just combined the fractions? So this was an s down here because one of the s's canceled. So if you combine the fraction, you get an extra s. Okay. All right, so let's take the derivative. So derivative of the numerator is just 3s squared. And minus the denominator times the derivative of the denominator, sorry, which is 1, times 120, s cubed plus 128,000 over s squared. Okay, so this is negative 2s cubed minus 128,000 over s squared. We have a 3, positive 2. We have a 3s cubed here, and then a minus s cubed, makes 2, and then minus 128,000. Okay, so let's factor out the 2. What is that? 64? Okay, that's nice. That's a perfect square. So s minus, how many zeros is in this one? 8. No, it's 2. Sorry. Oh, it's not a perfect square? Oops. No, it's not. Damn. Okay, I thought it'd been nice. Unless something went wrong. It's 80 times. Oh, okay. So it was 1 off. Alright, so can't do that. Alright, I feel like it should have been nicer though. Did something else mess up? 4 times 32 is 128. Alright, maybe it's just not a nice problem. Okay, so SA prime. Alright, so the nice 0 is square root of 64,000. The positive one. Alright, so if it's 800 times 80, then this is 100 times 8 times 80, 10, 8 times 8 times 10. So it's 80 square root of 10. All right, so that's S. 80 square root of 10. Okay, everyone agree now? Right, yeah, so, right, you just set S squared minus 64,000 to 0, and then we get 80 square root of 80. So we want to find both the dimensions, so we need the H as well. Okay, so not bad since we're going to be squaring it. So we know that 32,000 is equal to s squared h. So that means that 32,000 is equal to 80 times square root of 10 squared times h. So it's 80 squared times 10 h. So whatever that is. Oh, yep. All right, sorry. Thank you. Yeah, I somehow turned that 3 into a 2. Is 64,000 a perfect cube? It's close to one, right? Or maybe it's not. 4 cubed is 64, is that right? Yeah, it is. It's 40. So s. So okay. So let's factor it. S minus 40 s squared plus 40 s plus whatever 40 squared is over s squared. This is sa squared, sa prime. Okay. We probably should worry about these roots, right? Why or why not? Should we be worried about those roots? Right, we're solving for the roots of the derivative, right? So 40 is one of them. Do I care about these roots? No. Yeah, why? It is, yeah. In particular, when you factor the difference of two cubes, a cubed, or let's just look at it. Yeah, let's do x cubed. Whenever it's x cubed minus a cubed, you could use Rolle's theorem to show that it only has one real root, but also look at the discriminant of the quadratic term. What's the discriminant again? Do you remember the discriminant? This is useful for Rolle's theorem. I use a here, but you can just say the normal formula for the discriminant if you want. Yeah. So it's b squared minus 4ac, so in this case it's a squared minus 4, and the c is a squared. This is always negative. A squared times 1 minus 4, so negative 3a squared. So it's always true. Whenever you factor a difference of two cubes, it always factors into one linear and an unfactorable quadratic. So this is just a fact whenever you do the difference of two cubes. And why is this helpful is because you could just skip right to 40 from here. You know it's a difference of two cubes. It's also true for the sum of two cubes. The discriminant is the same. So just a good thing to know. They both have the same discriminant. But do you see that? So if you know that 40 is the perfect cube, you don't really have to go and factor everything. A difference of two cubes always only has one. It can only be factored this way, and this can't be factored further in at least the reals. Okay, so that means that 40 is the root of the derivative. And I don't need to say this, hopefully, but why don't I care about the roots of s squared plus 40s plus 40 squared? Like, they're complex. Those also are roots, but why don't I care about complex roots? Silly question. Why don't I care about complex roots when I'm trying to minimize something? I mean, the obvious answer is just like, what's I length? Like, complex, it means like stuff with I in it. So essentially, if you were to actually use the quadratic formula here, you'll get stuff with I in it. But imaginary S doesn't make sense, right? Because this is a real thing. Okay, so let's go back to our, so we have found 40 as one of the dimensions. So we have 32,000 is equal to s squared times h is equal to 40 squared times h. Okay, so that's 1,600. Everyone following? Okay, great. Okay, so that is, what, 20? Is that true? All right, so that's it, right? So our S is 40 and our height is 20. So this is the dimensions whose volume is 32,000. That minimizes a box with an open top. Okay. So questions on this one? All right, so let's go to the next one. Oh, here's a fun one. Find the point on the line y equals 4x plus 7 that is closest to the origin. Okay, so let's kind of draw a picture just to see like kind of what's going on. By the way, if you ever take matrix algebra, which I teach, there's a easier way to do this without calculus. So if you ever have to take matrix algebra, know that there is an easier way to approach this problem without calculus. But we're in calculus, so we're going to do it with calculus. So we want to find the point on the line that's closest to the origin. So there's a lot of points on these lines, right, that have some distance to the origin. We want to find the one that's closest. Anybody have any approaches? Just curious, actually, is anyone in matrix algebra now? I know some people take it coincident with Calc 1. Yeah, it's the one right before linear algebra. It's 160. It's pretty much linear algebra. All right, so yeah, so what are we minimizing here? Can someone say, like, in words, what we are minimizing? Kind of gave it away that I said minimizing. Closest to the origin, that's a minimizing word. Closest. Yeah, what are we minimizing? Yeah, good. We're minimizing distance to the origin. And yeah, it's the distance equation. What is the distance equation? The distance between the 2 points is what? I think it was square root, right? So you do the difference, x2 minus x1, square it, and the difference of the y's, y2 minus y1 squared. What formula does this look like, and why don't you need to memorize this? Because it looks exactly like this other formula. What is the distance equation? Yeah, it's just Pythagorean theorem. So no need to memorize distance formula because it's just the Pythagorean theorem. Okay, so one of these things is the origin, right? So we can just make this 0, 0. What's x2 and y2? What is that? Where is that in particular? Yes, they're points in the line on y equals 4x plus 7. Okay, so how do you simplify this? Right, it's two variables and you want one variable. So the hint is that it's that x and y are points in the line y equals 4x plus 7. Exactly. Right? What is y? Well, it's just 4x plus 7. So by the way, if this was any other curve, what would be differences in the replacement? So whatever curve you're minimizing to the origin, could be even any other point, this is your setup. So this doesn't change until you plug stuff in. All right, so your d of x, so you probably want to expand this, x squared plus 2, 4x plus 7, 4. Oh, whoa, I did a derivative. That's not squaring. Sorry, 16x squared plus 2 times 28x plus 49. So that is 17x squared plus 56x plus 49. Everyone agree with that? All right, so we're trying to minimize this, right? I'm gonna show you a really cool trick. Um, you don't actually need to take the derivative of this radical. Why not? Can someone guess why not? What can you do so that you can not have to take the derivative of the radical? Because radical is kind of annoying, right? You might have to still deal with the radical, but you can kind of get away with it if you do one step. Oh, yeah, you could do that. You would still have to deal with the radical. I like that in general. It's good for like easy chain rules. Yeah, you can just square it. You have to be careful though. When you take the derivative, what do you do with the d of x squared? Do you know how to take the derivative of this? So this little final review. What do you do with that? How do you take the derivative of d of x squared? Yes. It's just 2d of x d prime of x. This is implicit differentiation. Or chain rule, really. So then you just take the derivative of this side. It's 2 times 17, 28. No, it's not. Cannot multiply. 34. Thank you. So what is d prime? This thing that we wanted, right? It's just 34x plus 56 divided by 2, and then square root of 17x squared plus 56x plus 49. So yeah, we didn't actually have to deal with the derivative of a radical if we just use implicit differentiation. Okay. Cool. So, and if you notice, this now kind of look at it from above. That is what you would get, right? It's 1/2, by chain rule, 1/2, and then this thing would have a negative 1/2 exponent. That's down here. And then by the chain rule, it's the derivative of 34x plus 56. So by the way, everyone see that last step, I divided by 2d of x. Yeah. I think it's kind of neat, right? If you see something that's very intimidating, like square roots, you just get rid of it. As long as you're careful, you can just get rid of it and just do everything is just a power rule now. Okay, so we're trying to set this equal to 0, right? For minimizing. So what is that? X equals negative 56 over 34. Thank you. Negative 28 over 17. Okay. So, and then what's y? How do you find y? Oh, So two things. Yeah, how do you find y is one thing, and the other thing is, why don't I care about the denominator? Why am I ignoring the denominator here? Because what I can do, so now why can I ignore the denominator? Well, what's other critical points is when the denominator is equal to 0, right? But if the denominator is equal to 0, then d of x is equal to 0. Yeah, and it's never equal to 0 because, well, the line's not even on the origin. So who cares? And also, yeah, it should never equal 0 regardless. Okay, cool. So this is x, and how do you find y? Yeah, the original equation was 4x plus 7. So whatever that is. So that's the point. Of course, barring any computational mistakes, this is the method. It's not very a pretty point, but that's it. All right, so any questions on this? So usually when something's asking for the closest to something, you're usually probably going to use the distance formula. You can use implicit differentiation for a little trick. Yeah. Okay, so let's go to the... Oh, we can take a break. Why don't we take 5 minutes? Let's meet back at 6:45, and we can just do more. Okay, yeah, let's do this one. Yeah, so let's move back at 6:45, and then we'll work on this one. Ironically, this is actually kind of easier, and you may see why. You can ask me questions in the meantime. When is next quiz? Okay, so today is optimization. We might do a little, maybe we'll do some more optimization on Thursday. But we're going to do antiderivatives on Thursday. So, maybe a rough plan, either next Thursday or next Monday. Not the upcoming Monday, but the Monday after. If you don't mind spilling over into the next section, or sorry, what am I talking? Tuesday after. Oh, word problem for number 3. Was that from up here? This one? Or the third word problem we did? Wait, sorry, what? What do you want right now? The question itself, or the work? Oh, the work for it? This one? This was the work for number 3, for this one. This was number 3, and this was the work for number 3. The question, it's right here. Find 2 positive numbers whose product is 100 and whose sum is a minimum. Oh yeah, so quiz is either next Thursday or the Tuesday after. Probably safe bet. I'll probably make it Tuesday after just to give you some extra time. So probably could probably plan on that. Sure. Oh, just by the way, if you, I had more curve sketching problems. If you want to try them, if you really follow the steps that we did in class, these shouldn't be too bad. There's some other ones from the book that I just had there we didn't get to because it kind of takes a while to go through them. But if you wanted more curve sketching problems, there are some here. All right, let me just set this one up. We want to find the points on the ellipse that are furthest away from the point 1, 0. So, this is going to be a distance formula because it's furthest away. So we might need to be careful. So there's probably going to be multiple points. We have to be careful that we don't choose the closest point, right? That we keep the furthest point. All right, so it's going to be a distance formula because it's about distance. So someone tell me x1, x2, etc. Start with this point. What's x1 and x2? Or sorry, what's x2 and y2? So everyone back? We're still waiting on some people. All right, so we're trying to find points on the ellipse that are furthest from the point 1, 0. So one of these things, x2, y2, or x1, y1 should be 1, 0. Probably want to use x2 and y2. Instead of having to write out this square root the whole time, I'm just going to say d squared is equal to x1 minus 1 squared plus y1 minus 0 squared. Okay, now, someone say something about x1 and y1. What can you do? All right, well, notice that this is our equation of the ellipse, but we don't have to solve for y. We can just solve for y squared. That's that y squared is equal to 4 minus 4x squared. So it kind of saves us some hassle. Okay, So now we have a function d of x squared is equal to negative 3x squared minus 2x plus 4. Okay. Everyone okay with that? Yes, 1 plus 4 is 5. It is not 4. Thank you. Okay, so let's do it. We're trying to find the points. We don't know if it's minimal or maximal yet, but we'll find that out. So let's take the derivative. So using the trick, we don't have to deal with square roots just yet. So we have d prime of x is equal to negative 6x minus 2 over 2d of x. Okay, why don't I care about d of x? Oh, we can actually even simplify this. This is negative 3x plus 1 over d of x. Why don't I care about d of x equals 0? Now, actually, it might equal 0, but why don't I care about it equaling 0? Can you see where it is equals to 0? So what would it mean for it to equal 0? Let's say that. Yeah, if you just plug in 1, 0 into the ellipse, you get 4 equals 4, which that means it's on the ellipse. So why don't I care about d of x equal to 0? So the other one, it's never going to equal 0, so that's why we didn't care about it. But why don't I care about it here? So think about the wording of the question, the two questions. So in this case, I didn't care about it equaling 0 because, okay, it's not even on the curve. But I might care when it's equal to 0. However, in this one, even though I know it's equal to 0 somewhere, I don't care about it. Exactly, yeah. I want the points that are furthest away. So I don't care when d of x is equal to 0. Okay, so what is x? X is equal to negative 1/3. Okay, cool. Let's just verify this is a maximum. What do you know about d of x? Is it positive or negative? So think simple for this question. Is d of x positive or negative? So when I'm test valuing, why do I claim that you always know the sign of d of x? I think really simple. I'll give another hint. This is always positive. Why is it always positive? Actually, should probably even put 0 here. Why is d of x always positive? Sorry, no. 1. Yeah, so not only is it a square root, but it's distance, right? Distance is always positive. And yeah, the square root makes it positive. Okay, so when you do test values, you don't have to plug anything into this annoying radical, right? All you have to do is do test values around it. Okay, so let's plug in 0. This is negative. And let's plug in, I don't know, negative 1. This is positive. So it truly is a max. Right. So, I mean, we only had one value for x, so obviously, right, if it's asking for the farthest point away, then this should be okay. Oh, by the way, if you plug something in, oh, right. Yeah, okay, so this is a max. So what's the y value? Be careful. So you want the points on the ellipse that are furthest away. How can you determine the y value of the points? Yes, plug x into the ellipse equation. So while I'm doing that, can someone tell me why I have to be careful? Why am I asking you to be careful here? Yeah, the square root. I'll actually get 2 values. So y is equal to plus and minus. Square root of 32 is equal to 8 times 4. Right? Four square root of 2 over 3. Yeah, so it's definitely over 3. 4 square root 2. Oh, why did I say 4 squared? This is, yeah. 4 squared times 2. Yes, good. So plus or minus 4 root 2 over 3. So our 2 points are negative 1/3, 4 root 2 over 3, and negative 1/3, negative 4 root 2 over 3. Why don't I care about positive 1/3? That always also makes this equation true. Because that's not what makes it maximal, right? Negative 1/3 makes it maximal. Okay, so let's kind of just draw this as a picture. All right, so let's draw the ellipse. So you have 4x squared plus y squared is equal to 4. So you have the point 1, 0. And we had these maximal elements, maximal distance, negative 1/3. It's been a while since I drawn ellipses. So actually, let me plug it into Wolfram Alpha. Let's see what they say. Give me a second. I just want to see this. Okay. Okay, so the ellipse is actually more like an egg, so it kind of looks like this. All right. Yeah, the y value has the bigger axis. So these are the points that are furthest away. Okay. Okay, so any questions on this problem? So kind of get the idea. So we have distance, square root, and I like this just square both sides trick as long as you use implicit differentiation. All right. I want to do this one first. Okay, let's do a cylindrical can without a top and is made to contain some amount of liquid. So find the dimensions that will minimize the cost of the metal to make the can. Okay, so info. Cylindrical can without a top. It contains V amount of liquid, and you want to minimize the cost of metal. Okay, so what do we know? So we're coming up with like a formula, right? Not a specific value of volume. We're going to make up the formula that will minimize the cost. All right, so we need, anyone know the volume of a cylinder? Yes, pi r squared times height. So notice that, R and H could change and have the same volume. So that's why this question is somewhat interesting. Okay, so what we want to do is to find the dimensions that minimize the cost of metal. What tells you minimizing cost of metal? What formula do you think that implies? Surface area. What's the surface area of the cylinder? Good, yeah. So the surface area, so that is true in general. In general, it is 2 pi r squared. 2 pi r squared, why? Because that's two areas of circles. And then plus 2 pi r h is because when you unravel this, it makes a rectangle of height h, and the length is actually just the circumference of the circle, just 2 pi r. So that's true in general, but what formula do we want to use for our problem? Claim that's it's a bit different. Good, yeah. So one of the pi r squareds just gets taken away because the top is open. So just pi r squared plus 2 pi r h. Okay, so this is what we want to minimize. Okay, so we have SA of r and h, right? These both can be changing. Pi r squared plus 2 pi r h. How do we turn this into a one variable problem? Remember, v is constant, by the way. I think solving for h would be better, honestly, because we would have the square root to solve for r. If this r wasn't there, then I would agree that probably r squared is the easier one. But because we have this r here, I would think solving for r would be kind of annoying. So I like solving for h, actually. But you see that? Like, you'd have to, like, square root. Okay, so just simplifying this. So even more, just get rid of these pi's. Sorry, we have 2v over r. Okay, so even more, we could do combine fractions. And we get pi r cubed plus 2v divided by r. Okay, so any questions on those steps there? All right, so let's do it. So we want to take the derivative. So remember, v is a constant. So the derivative of the numerator is 3 pi r squared, then times the denominator, minus the derivative of the denominator times the numerator. Okay, so we have 3 pi r cubed minus pi r cubed minus 2v over r squared. So this is 2 pi r cubed minus 2v over r squared, or 2 times pi r cubed minus v over r squared. Okay, so what's the critical number that you care about? Someone give me a critical number, in fact. So what would a critical number be? Or what would be the setup, at least, if you can't do it immediately? Like, what would be your step? Yeah, you just set the numerator equal to 0, right? We don't want r equal to 0 because that doesn't make sense. That means volume wouldn't be a thing. So we set the numerator equal to 0. So pi r cubed minus v. Oh, I'm sorry, not SA of v, SA of r. That was confusing. V is constant. So r cubed is equal to v over pi. So r is equal to cube root of v over pi. So that is it. That's r that minimizes the surface area. So now we need to see the height, right? All right, so if v was equal to pi r squared times height, we just found out that r was this cube root of v over pi, then we can find height. So this is v over pi is equal to cube root of v over pi times height. So I could cube both sides to get rid of that cube root. So your v over pi squared is equal to h cubed. And you have cube root of v over pi squared. Thank you. Okay, how bad does that mess it up? Okay, this is squared. Cubing is still okay. This would be squared. So this would be 1 and 1. So cube root. All right, so that means that r and h are of the same dimension. So r is cube root of v over pi, and h is cube root of v over pi. Okay, so this is nice because this gives you a formula, right? So if you have a can of, what's a nice cube root? 1,000. So if you have a can that holds 1,000 milliliters, right? If you want to minimize your cost, r would equal 10 over cube root of pi, which I guess is not as nice. And h is equal to 10 over cube root of pi. So you want your radius and height to be the same. So any questions about that? So maybe it's a bit harder because there's a v in here, but if you just treat it as a constant, then it's fine. Okay, so any questions on this one? All right. Okay, so I'm going to give you the formula for surface area for a cone because it's not that fun. But given that the surface area of a cone is pi r times r plus square root of h squared plus r squared. So that is the surface area for a cone. The volume's not as bad. Okay, so you have a cone drinking cup that's made to hold 37 centimeters cubed volume of water. By the way, we actually might derive this formula later in this class, the surface area for a cone. So kind of get excited for that. So find the height and radius of the cup that will use the smallest amount of paper. Does anyone remember the volume of a cone? Volume is the easier one. Yeah, it's 1/3 the cylinder. So it's kind of a fun fact that if you take a cone inside a cylinder, the cone takes up 1/3 of the volume. The other 2/3 are like, this is 3D. The other part takes up the surrounding part of the cylinder. So it's 2/3 of it. Yeah, so it's 1/3 pi r squared times height. Okay, so you have the cone that's made to hold 27 centimeters. We'll just call it 27. So 27 is equal to 1/3 pi r squared times height. And what we want to do is minimize the surface area. Okay, so what do? So we have that radical expression for surface area. Unfortunately, you can't really do a square both sides trick as nicely because you have a sum. Yeah, what do you want to do? How do you minimize a? How do you get that into one variable? Always the step of these optimization problems is turn into one variable. What do you want to do? Last one, then we're done today. So I think we should solve for h. Right, so we can ignore square roots. So what's 27 times 3? It's 81. So 81 over pi r squared is equal to h. So now our surface area function is pi r, I'll just distribute it, pi r squared plus pi r square root of 81 over pi r squared plus r squared. Okay, so we have to take the derivative of this. Actually, let's actually do a little trick. Actually, no. I was trying to get rid of the radical, but I don't think anything nice would work. Okay, so let's take the derivative. So we have 2 pi r. And how do I take the derivative of this expression here? And we can simplify this a bit for taking the derivative. It's 81 squared plus pi squared r to the 6 over pi squared r to the 4th. This is all square root. So that means your denominator we can simplify this to pi r squared plus, so notice that when you take the radical of the denominator, the pi r cancels out. You get 81 squared plus pi squared r to the 6, and then your denominator, you're still left with an r. Everyone see that? So what I did here was I combine fractions. And this step here, we're left with pi r and then divided by square root of pi squared r squared. And then pi r, r to the fourth, r squared. That's why we're left with an r. Okay, so when you take the derivative, notice that we just got rid of the product rule, right? So now we can just deal with one quotient rule instead of having to do a product and then a quotient and a chain. So we simplified it down to something a bit nicer. Okay, but it's still kind of messy. All right, so the derivative of this is 1 over 2 square root of 81 squared plus pi squared r to the 6th. And then the numerator is 6 pi squared r to the 5th. So all times r minus 1 times square root of 81 squared plus pi squared r to the 6th, all over r squared. Okay, so we can cancel this and make a 3. So when we combine fractions in the second part, we get 3 pi squared r to the 5th minus 81 squared plus pi squared r to the 6th over square root of 81 squared plus pi squared r to the 6th all over r squared. Okay. That's 2. Okay, so negative pi squared r to the 6th plus 3 pi squared r to the 5th minus 81 squared. Then we have r squared square root. All right. See, is everything okay so far? Seems that. All right, so combine fractions. We won't have time to finish this one today. We get 2 pi r cubed, then 81 pi squared r to the 6th, then minus pi squared r to the 6th, plus 3 pi squared r to the 5th minus 81 squared. Yeah, something. All right, we're running out of time anyway, so next time I'll see what happened, and maybe it's not as straightforward, but I'll finish this next time, and we'll try to come up with a way to kind of make this easier. Anyway, you have a lot of examples to work with that should help you out. But okay, I'll see you Thursday. We might do 1 or 2 more optimization problems like this, and then we're going to move on to antiderivatives. So to kind of get you thinking about antiderivatives, it's a way to undo differentiation. Oh, am I muted? Can you hear me? Okay. Can't hear also. Um, we're done. Let's see. Time is doing antiderivatives as a way undo initiation. A couple more optimization. I'll finish this problem next time. All right. Sorry if I got muted towards the end there, but we're at the end anyway. So I'll see you next time. Maybe if one of you can do this and maybe see maybe if I went wrong or did a bad step or just had to keep on going. Yeah, let me know. Work on that. All right. Yeah, I'll see you Thursday. Keep working on the homework. Yeah, see ya. Bye.